Picture an atom. You are probably imagining a tiny solar system, a tight cluster of protons and neutrons in the middle, with electrons zooming around them in perfect elliptical orbits. It is the universal symbol for science, stamped on textbooks, corporate logos, and comic book heroes. But as a physical object, it is a complete physical impossibility. According to the strict laws of classical physics, a charged particle like an electron accelerating in a circle has to radiate energy. If an electron were actually orbiting a nucleus, like a planet around a sun, it would constantly bleed off that energy. It would lose speed and within a fraction of a second, spiral violently straight into the center. If atoms actually operated under those classical planetary rules, every single atom in the universe would collapse almost instantly. Matter wouldn't hold its shape. You, the chair you're sitting in, and the Earth itself wouldn't survive a single second. This flawed picture started in 1911 with a physicist named Ernest Rutherford. Before him, scientists thought the atom was a solid sphere of positive charge, dotted with negative electrons, like a plum pudding. Rutherford shot a beam of radioactive alpha particles at a sheet of gold foil. Most particles passed right through, but a few bounced back. He realized the atom wasn't solid at all. The atom, he discovered, was almost entirely empty space. The positively charged core, the nucleus, is 10,000 times smaller than the full width of the atom. If the atom were the size of a massive football stadium, the nucleus would be a single marble sitting on the 50-yard line. The electrons orbit somewhere in the upper deck. Rutherford correctly proved that physical objects are 99.999% empty space. But to explain the arrangement, he proposed the planetary layout. Without realizing it, he built a mathematical model that dictated our own immediate destruction. 2 years later, a young Danish physicist named Niels Bohr joined Rutherford's lab. Bohr saw that the classical rules were dooming the atom, so he decided to write new ones. Bohr proposed that electrons are not free to drift anywhere in that vast empty space. Instead, they are locked into distinct shells, or specific energy levels, surrounding the nucleus. As long as an electron stays in its designated shell, it doesn't emit any energy. It simply exists there, perfectly stable. But electrons can move between these shells. When an atom absorbs or releases energy, the electron makes a move. It doesn't travel through the empty space between the rings. It disappears from one shell and instantly snaps into another, releasing a discrete packet of light. This is the origin of the term quantum leap. Over the next decade, this idea evolved into the quantum mechanical model. By the late 1920s, physicists like Erwin Schrödinger and Werner Heisenberg realized that electrons don't travel in neat, circular tracks at all. The tracks were replaced by three-dimensional probability clouds. You can never know exactly where an electron is, only the mathematical likelihood of finding it in a given region. This introduced a highly uncomfortable concept. At the most basic, subatomic level of reality, certainty does not exist. Exact locations and momentums are impossible to pin down at the same time. The physical building blocks of the universe are governed entirely by statistics and chance. Bohr's quantized energy levels successfully explained why atoms are stable. He saved matter from collapsing in on itself. But the cure for Rutherford's paradox required abandoning a predictable, clockwork universe. Not everyone accepted this new reality. Albert Einstein, the man who had already rewritten the laws of gravity and time, looked at quantum mechanics and saw a deeply flawed theory. Einstein built his career on a strict cause-and-effect universe. If you know the starting conditions of a system, you should be able to calculate the exact outcome. He refused to accept that the deepest layer of nature relied on random probabilities, famously declaring that God does not play dice with the universe. The tension came to a head in Brussels at the 1927 Solvay Conference. Nearly all the leading physicists of the era gathered to debate the new quantum rules. It quickly turned into a daily, intellectual boxing match between Einstein and Bohr. Every morning at breakfast, Einstein would launch a meticulously designed thought experiment. He would invent hypothetical scenarios, slits on tiny springs, measuring devices capturing recoil, all engineered to measure exact particle properties simultaneously and bypass quantum uncertainty. Bohr would spend the rest of the day in a state of high agitation, pacing his room and working through the math with his colleagues late into the night. By dinner, he would present a flawless rebuttal, demonstrating exactly how Einstein's own hypothetical measuring devices would inherently disturb the system and preserve the uncertainty principle. 3 years later, at the 1930 Solvay conference, Einstein arrived with an incredibly sophisticated trap. He proposed a sealed box suspended on a spring scale, containing a clock hooked to a mechanical shutter. A single photon of light would escape at a precise time, and the scale would measure the exact change in mass, theoretically giving both the time and energy of the photon with absolute precision. Bohr was initially stunned, but after another sleepless night, he found the flaw. As the photon leaves and the box moves upward on the spring, its position in Earth's gravitational field changes. According to Einstein's own theory of general relativity, that shift in gravity alters the rate at which the clock ticks. That slight time dilation introduced the exact amount of uncertainty required by quantum mechanics. Bohr had defeated Einstein using Einstein's own equations. These debates were intense, but they were never personal. They were high-stakes battles over the very nature of existence, debating whether an objective physical reality exists independently, out there in the dark, when nobody is looking. In 1935, Einstein launched his final major offensive. Along with 2 colleagues, he published the EPR paradox, taking aim at a phenomenon known as quantum entanglement. According to the math, 2 particles can become entwined so heavily that measuring one dictates the state of the other. Einstein pointed out that if you separate these entangled particles by millions of miles, measuring particle A would instantaneously alter particle B. He called it spooky action at a distance, arguing that since nothing can travel faster than light, quantum mechanics must be an incomplete theory, missing hidden variables. Bohr replied with the principle of complementarity. He argued that Einstein was assuming the particles had fixed properties while flying through space. In the Copenhagen interpretation, the particles don't actually have a defined position or spin until you measure them. They exist only as probabilities. The act of applying a measuring device literally forces reality to take shape. Einstein remained unconvinced. He spent the remaining decades of his life working in relative isolation, trying to construct a unified field theory that would restore strict classical causality to the universe. He never found it. But his relentless attacks served a vital purpose. By constantly searching for fatal flaws, Einstein subjected quantum mechanics to the most rigorous stress tests in scientific history. He forced Bohr and the quantum pioneers to refine their arguments, ultimately leaving the theory mathematically bulletproof. Which brings us back to that classic planetary image of the atom. It feels intuitive, it makes sense, but it is a comforting illusion. The device you are watching this on, the chair beneath you, and your own body are 99.999